Hello to everyone. I'm glad to see you again. This is our third lecture in this course, and I'm happy that we will learn something new. So today we will talk about using of external sensors in GDV bioelectrography. Probably you have already heard about some of them, like Sputnik sensor, water sensor, BioWell glove, that are available um, for anyone to buy. And we will discuss today how they should be properly used, what kind of data we will get, and how to make interpretation of this data. So all this together is the essential part of making experiments with these sensors. So let's begin. And the first reference that I want to make, and the first thing that we will talk about is about physics. So we will have to understand what it's all about. So let's begin, and let's look at the presentation that I've prepared for these purposes. Here we are. Let's go. So in essence, of course, the physics of capturing and measuring fingers, or that we have already discussed earlier, or the physical principles of capturing the metal cylinder, the calibrator, are the same. So we already know about this electronic avalanche, etc. And here is just another case. It's the sensors, different sensors that you can connect to this metal cylinder. Well, it's nothing difficult here, so let's go step by step. Once again, what do we measure? The physical principles. So this is light. So the main parameters of light are area intensity, well, and of course the resulting energy as the multiplication of area times intensity. There was another aspect that we were analyzing with the fingers, the structure of light. And of course, in case of fingers, the structure of light and the patterns that we were discussing and that you have heard in different other lectures on this course is not so useful in case of using sensors. Because in case of the external sensors, you're capturing not the fingers, but the metal cylinder. And as long as there are no acupuncture points, no energy meridians there, the glow is uniform and usual, the same around all the surface of the metal cylinder. So no need to analyze the pattern. So the only thing that is left for us are these three parameters: area, intensity, and energy. That's it. Well, this is from what we have started long ago. So we had only these parameters, but we will talk about other parameters that are being derived from this in the software. Well, during this process of development of the BioWell technology, GDV technology, we have found out that the stability of the results in work with external sensors is dependent on the type of the cylinder that you are using. So in first models of the BioWell, there was a stainless steel cylinder, and the tip of it was made from titanium. But it turned out that this titanium leaves some traces on the surface of the glass electrode, and of course it then um, perturbs the scans that we get. Not so good. And then we started using, because of that, simply stainless steel cylinder, and it turned out that the results and the stability of the measurement is highly dependent on how polished the surface of the cylinder is, not only on the bottom part, but also on the walls of the cylinder. So, and we don't need excessive disturbance and variability in the signal just because of the cylinder, because that's not what we are interested in. And nowadays we have this latest model, Type C here, of the calibration cylinder. That is a thin metal tablet on the spring. So that's the best calibration tool insert to use for measurements with external sensors. So that's what I have here. Well, you remember already this scheme, and we have been discussing this in the previous two lectures that we had. The main thing here is that, again, you remember these graphs, the amount of light that we get, the intensity of light that we get is dependent on what is connected to the metal cylinder, to the calibrator. So you see in this case, you see the graph of the dependence of the capacitance of external circuit, and you see the dependence of area on the capacitance, so how much light we get. And I will give you the practical demonstration once again for you to really grasp this and understand what it's all about. Another graph about average intensity of the brightness of the image that we get dependent on the capacitance. Well, the same story about resistance of the object connected to the calibrator, for intensity and for area. So the result is that increase of capacitance leads to increase of area and intensity, increase of resistance leads to decrease of area and intensity. Any additional object connected to the calibration cylinder will lead to increased capacitance. Let's try to understand what does it mean in real life, because it's all words, and I know that in theory maybe it's hard to understand what it's all about, specifically if you don't have a technical education. So we will do together with you a small experiment in real time, so you can see what's the essence of this. Let's open the Bible software and take a look at the real-time experiment there. So close the presentation and we go to, here we are. Well, of course, first thing always to do is to check if the glass electrode is clean and if the device is calibrated. So that's what we will do right now. We go to calibration and fix that. It takes only 16 seconds to do the calibration. Everything will be processed and saved on the server so that we can easily continue our work with external sensors. So this is done. Let's go to environment mode. let's select that the device will be capturing every 1 second, or like maybe 2 seconds is enough for us. It's okay, click, and we will be concentrated mainly on the area graph, so it will be full screen for us. So let's click start. So here we see the image. You see it's very big and bright now because the cylinder, the calibrator, is connected to the ground of the device. So let's see what it will show to us. So if you look on the graph, you will see that the average area in the beginning is 12,400 pixels, or somewhere around that. So it means the device is calibrated correctly. That's exactly 12,300 that we are tuning and during the calibration, and having it near 12,400 is almost perfect, because 100 pixels is not a big deal in terms of the deviation from the norm. So, well, you can understand that 1% is 124 pixels. So if it's less than 100 pixels, so it's less than 1%, right? So as you see, the average is where we want it to be. And of course, depending on what is going on around, this value will be oscillating. So as long as these are electrons, this is gas discharge, it cannot be absolutely the same in a long period of time. It's impossible. Of course, it's changes in time, but after some time, the air under the cover will get to some saturation level, and the curve that we see on the screen on the area graph will also become more stable. And of course, if I touch it, if I connect the touch with my hand the wire, or I move the device, the result can slightly change. But, well, you need to understand one very important thing, is that when you have this calibration cylinder connected to the ground, it's that infinite number on the graphs that we were looking at about the capacitance and resistance of the external circuit. So that's the maximum that device can get at this level of voltage that is being set in the hardware level. So you cannot get actually 15,000 or 20,000 pixels. Well, first of all, because the physical properties of the device stays the same, and physical properties of the air stay the same. Only if you change the air properties, chemical, physical properties, then the area and the intensity, henceforth energy parameters, can change. But if the air stays the same, the parameters will not move anywhere, and they cannot get higher because you don't change the voltage. And in this case, well, let's check and do a real-time experiment. So we will just connect additional wire. You see this pretty long wire. You see no reaction. Everything stayed at the same level. So just adding this long wire didn't change drastically the value. Well, you see it's oscillating still at the same region, around 12,000, 12,200 pixels. No big difference. Once again, if you come back to this graph, you look at it, you will see that after some level there is a saturation happening, and no matter what else you connect there, what else is being placed on the electrode additionally, the number of pixels, the area will not increase. So this is the ceiling, higher than which you cannot jump at this level of voltage that is being set during the calibration. So let's return back here and make another experiment with it. So now I will disconnect this big wire additionally connected from here and from here. It's disconnected. So now I will just disconnect the wire from the earth or ground axis of the wire. Let's look where it will lead us. You see, now it's hanging in the air, and you see that now we have something around 4,400 pixels, or even a little bit less. So, important moment. Now I will connect myself, my fingers, to this wire. So, look, I'm taking this wire. You see the area has already slightly increased just because I'm touching it, even through isolation, because still even through isolation there is an electrical capacitance that I have. If I disconnect myself, it should go slightly down. Now I'm connecting myself, look. Now my capacitance is added to the electrical capacitance of this wire. And you can see that now our sum capacitance is around 10,000 pixels, right? So you see, my input is something around 5,500 pixels, right? It was 4.5, now it's 10. So it's 5,500 pixels. My body is equal to 5,500 pixels. I disconnect myself and it returns back to the ground position, initial position. Now, instead of myself, I will increase the capacitance by adding wire. So I will be connecting this wire here, one, and now it's all connected. I'm not touching it now, I have dropped it. So you see that just adding this wire has led to increase of the emission 3,000 pixels. Me, as a very big body with very high electrical capacitance, I have led to 10,000 pixels, and that's my top score. Whilst this small wire has led to already 7,500 pixels. So this is once again, this is the demonstration that the dependence is not linear. It's like this that you see on the graph. So when the glow is very low, even small piece that you add there, small increase in capacitance leads to a huge increase in pixels in area. Whilst if you add a very big object, but it's already in this area of the closer to saturation, then of course the difference is not so big, and that's what we see on the screen here. So again, you see that now I can connect myself to this wire that I have connected to the previous wire. So 2 wires plus me will give us same amount of pixels. Again, around 10,000 pixels. Why? Because in comparison with my capacitance, this capacitance is really small, very small ones. So, and you see that that's maximum that I can do in this aspect. So, but you see that in this case, when we were at 7,500 pixels, and I have touched and connected myself, you see the previous time I have added 5,500 pixels. This time it's much less. Let me demonstrate it here. As you can see, in the first case, when I touched the wire, the increase was this big, 5.5 thousand pixels. So you were assuming, I was agreeing with you that it's my capacitance leads to increase of 5.5 thousand pixels. But you see that here, instead of jumping for 5.5 thousand pixels, no, in this case, it's also me. Here it's me, and here it's me. Then here it's not 5.5 thousand pixels increase. Here it's from 7.5 to 10,000. It's only 2.5 thousand. So looking at this graph, what do you think? In which case you're working in a more sensitive region of the equipment? Of course, when connecting some object gives you big shift. So it means that at that, when you work here, the device, the system is more sensitive than when you work here. It's almost twice less intensity. So when you're working here, that's perfect. Very sensitive position. So that's the essence of doing the experiments in terms of tuning the device to the proper level. It means that the wire that you connect to the biweld shouldn't be very long. So if you want to put Sputnik or any other sensor several meters away, be careful with the fact that the sensitivity will decrease. Once again, if we look at the presentation here, look at this graph, see that it's the most sensitive region of work is here. But here, even enormous change in the capacitance, so just huge changes happening in the environment or in the substance that you are measuring, will give you very small change in the depth. That most probably you will not see because the noise level will be higher than this useful signal. Of course, the best place to work when even small change, or say for example the same changes in 50 picofarads, will lead to this shift in the results. So we know that there is a ceiling. So we have seen it, for example, in this case, when I'm working, it is around 10,000 pixels. I'm not talking about connecting to the ground exit. So it's around 10,000 pixels. What is the bottom? So of course, at some level, if there will be not enough capacitance in the internal circuit, maybe the gas discharge itself will not happen. So if I disconnect this big wire and I disconnect this wire too, what happens? The electrical capacitance is not enough for the device to give any gas discharge. So it is trying to do that, but it's not able to. So we can try to connect a smaller wire, for example, this big. Still, it's not enough to have a gas discharge. So we'll connect with standard wire, and here we have at least some emission. So, in fact, the edge of the gas discharge that can be given in biowell is somewhere around 3,000 pixels. So below 3,000, the gas discharge will not appear at all. So it means there's no sense in trying to tune the device to this. So, and of course, when you're working with some external sensor, I will demonstrate it here, that if this is the floor, and this is, well, that's maximum, but here is the ceiling. This is the corridor in which we can work. Yep. And of course, well, I will not recommend you to work here in this region, because if something changes, you can easily drop down to this floor level and the gas discharge disappears and goes to zero, and you lose the you will not see anything. So of course, it's better to have some kind of gap, some insurance that the results will be stable, and it means that you will have some distance from the floor and you will have distance from the ceiling. So approximately, I would say that one of the best options to tune your device to the level where it will give you something around 6,000 or 7,000 pixels. So in this case, if you work in this region, if you work in this region, it means that you will get pretty sensitive results. So it will be reacting to different changes, even simple ones. So there is some distance to go downwards if anything changes, for example, environmental changes or the air changes itself. And of course, you have a pretty big distance to ceiling. So for changes to take place, you will see that. Of course, you will not be hitting your head on the ceiling like we've seen here. how can we get this when we are working? So you see that at the present moment, when we have only this wire connected, it's something around 4,000 pixels, and it's dangerous to work at this. Of course, it's super sensitive region, but it's too close to the threshold, so it can drop down to zero. So we could take Sputnik now. And we will connect it to metal sync. If I take the wire that connects the Sputnik, I insert it to one side. The other side. What do we have now?